The interpretation of your correlation must be guided by the assumptions and parameters of the other correlation coefficients that we've introduced. Spearman's rho, or maybe the point by serial correlation, and the phi coefficient. In the same way that our other parametric statistics have required normality for the interpretation of their tests of significance, Pearson's R also requires that your data be normally distributed. However, because there are two variables involved in your correlation coefficient, Pearson's R requires that you demonstrate bivariate normality. In other words, it's not enough that both variables be normally distributed. They must be normally distributed when they're added together. You can envision the assumption of bivariate normality as being a three-dimensional normal distribution, a three-dimensional mound, as opposed to the two-dimensional mound-shaped distribution that we've been looking at in our previous statistics. As you can imagine, the testing of this assumption requires statistical software, and the testing methods that you might use are at least a little bit equivocal within the literature. We'll be assuming bivariate normality for all of our calculations in this course, but it's something you should think about when you start to analyze your own data. The assumption of homoscedasticity refers to the assumption that the variance of the errors around each value of x are roughly equivalent. In other words, the standard deviation of y is the same for each value of x. Again, this is an assumption that's difficult to demonstrate without the use of statistical software, and so we'll assume that the assumption of homoscedasticity is met for all of our calculations in this course. Residuals are the differences between the predicted values, i.e., the values that fall on the line of best fit, and the observed values within the data. We expect that errors will occur in any calculation of Pearson's R, but we need those errors to be independent or uncorrelated. It sounds like this is becoming a theme on this slide, but this is another assumption that isn't worth testing by hand. You'll need to use statistical software, like R, in order to test it. We'll assume that this assumption is met as well. Pearson's R is a scaleless descriptive statistic. You'll recall from our discussions of the coefficient of variation that scaleless statistics are calculations that do not change depending upon the overall magnitude of the values within the data. The reason that Pearson's R is scaleless stems from its definitional formula. The correlation coefficient is really just the standardized covariance between x and y. By dividing by the product of the standard deviations for x and y, Pearson's R takes the scale of both variables out of the equation. You can demonstrate that this formula simplifies to the sum of the cross product of z-scores divided by n-1 when the z-scores are calculated using the unbiased estimate of the standard deviation, i.e., the version of the standard deviation calculation that uses n-1 in the denominator. Of potential historical interest, the name product moment coefficient is related to this definitional formula. It makes more sense when you learn that the first moment of the distribution is the mean. This is where the moment part of the statistic name comes from. You can think of the correlation as being equal to the average of the cross products of the z-scores. We don't usually calculate the correlation coefficient using the conceptual formula. This would require us to first calculate z-scores for all of our data and compute cross products for each pair of observations. This would be time-consuming, especially for large data sets. Instead, we use the computational formula shown here. The statistical significance of Pearson's R is evaluated using a t-test with degrees of freedom equal to the number of pairs minus 2. We subtract 2 from the number of pairs in our data to account for the fact that we have 2 variables in the analysis. Although it is possible to calculate the t-test by hand, and your text describes methods for doing so, the most typical way to test the significance of Pearson's R is to look up a critical value of R on a table. And I've provided you with a table of critical values of Pearson's R on OWL. After we discussed correlation, we related this concept to the topic of linear regression. Whereas correlation was just interested in describing the relationship between two variables, regression is oriented towards the description of the extent to which x can predict y. In this context, x is cast as the independent variable, or the predictor variable, and y represents the dependent variable, or the criterion variable. In this way, regressions involve identifying a prediction equation that allows us to interpolate within our data. This is a term that bears further explication. Interpolation refers to our ability to predict a variable based on other variables around it. Extrapolation, on the other hand, involves predicting a dependent variable for a value that falls outside the range of x values for which you have data. Extrapolation can result in some wildly inaccurate predictions, owing to the fact that you're generalizing beyond the range of data that you collected, and so you're assuming that the relationship is the same in this extension of your observations. Sometimes it is, sometimes it isn't. In general, extrapolation is a risky proposition. As you might guess from the term linear regression, we're going to start with regression as it relates to a straight line. So this means that simple linear regression refers to the analysis of a straight line passing through a data set in such a way as to best predict the values within that data. The line of best fit is the line that best fits with our data in terms of minimizing error in the prediction of y using x. The general form of the simple regression line looks like this. Y hat equals b1x plus b0. Y hat is the predicted value, the value of our criterion variable that we would predict, given values of b1, the slope, and b0, the intercept. I honestly don't even remember when I heard that slope is equal to rise over run, but I don't know that I've met anyone who doesn't know this definition of slope. But this is useful for our purposes. It reminds us that the slope is equal to the change in y divided by the change in x. Consider what you end up with if you substitute 1 for the run in this equation. It illustrates a fundamental concept of regression, that the slope is equal to the change in y for every 1 unit change in x. Most of the time, however, we're working from numeric data, and we need a way to plot that line of best fit in order to be able to calculate a slope of the line. Turns out that we were nibbling around the edges of the concept of slope when we introduced correlation. Correlation is a scaleless coefficient because it controls for the variability of both x and y within the covariance of x and y. And we showed that it did this by essentially converting both variables to z-scores. With slope, we don't really want to standardize our values. We have a value for the intercept, so we don't necessarily need the line to pass through the origin. We can leave the variability of y in the value that we calculate for our slope. So our formula for slope looks like this. It is, effectively, the variability of x and y, the covariance of x and y, divided by the variance of x. You could also calculate this in a way that reintroduces the variability of y into the value for the slope. These formulae are entirely interchangeable. It really depends on the information that you have at your disposal. This is, of course, only the first part of the equation. We also need to calculate the intercept. This is the point at which the line of best fit crosses the y-axis, and we calculate this by taking the average y value and subtracting from it the average x value multiplied by the slope. So how is slope really different from the correlation coefficient? Well, take a look at the line of best fit drawn through a scatter plot of raw scores. The line of best fit doesn't go through the origin. It crosses the y-axis at the y-intercept. Now, if we were to convert x and y to z-scores and plot them in a scatter plot, the pattern of values stays the same, but the variables have been scaled to have a mean of 0 and a standard deviation of 1. And this has the effect of forcing the line of best fit to pass through the origin. As you can see from the formulae that we just introduced, if you standardize your regression line, i.e. you convert each of your variables to z-scores, your slope will be equal to your correlation coefficient, because the standard deviation of each of your variables is now 1, and your y-intercept will be equal to 0, because the mean of each variable is equal to 0, and this zeroes out the equation. To summarize, the slope of an unstandardized regression line need not be between -1 and +1, because the variability of y has not been removed. It's not a scaleless coefficient, and it's not equal to the correlation coefficient. If you were to convert both variables to z-scores before computing the regression between the variables, this standardizes the regression, forces the line to pass through 0, and produces a slope that is equal to the correlation coefficient. And conceptually, the slope is the amount that y will change with each 1-point change in x. This tracks back to your very first intuitive definition of the slope, rise over run. The slope can be thought of as the amount of rise for every single point of run. And finally, we identify the significance of a regression line by testing the significance of the correlation between the two variables using the Pearson table with degrees of freedom equal to n-2. In the second half of the course, we introduced count data and then generalized our test of means to the case in which we have more than two groups within our design. Let's review the material that we covered in weeks 7 through 10. In weeks 7 and 8, we introduced analyses that were based on categorical data, sometimes called count data. We also introduced some important features of count data that needed to be satisfied in order to be able to apply our analytic methods effectively. Most notably, categories must be mutually exclusive and exhaustive. Categories are mutually exclusive when a person cannot be in more than one category at the same time. So if you have established a dichotomous outcome variable with the categories yes and no, mutual exclusivity would require that you not allow your participants to respond with both yes and no. Categories must be exhaustive with regards to the classification of subjects in your data. This means that you can't just leave some of your participants unclassified. So if you're putting people into the categories yes and no, it's important that you consider whether or not that third option of yes and no is a reasonable outcome. If it is, then maybe your variable needs a third option for undecided. This is allowed for variables that are not required to be dichotomous, provided that the fundamental principles of exclusivity and exhaustiveness are still met. The simplest form of count data is the dichotomous variable. Male versus female, yes versus no, agree versus disagree. Because there are only two categories with this type of data, it can be described using a proportion, for example, the proportion of people that said yes to a particular survey item. The sample proportion is described using the symbol p hat, and the most commonly applied research design that is used to compare proportions is the binomial experiment. There are a number of essential characteristics of a binomial experiment. A binomial experiment has a set number of identical trials. There can only be two possible outcomes for each of these trials. The two outcomes must be both mutually exclusive and exhaustive, and the probabilities of occurrence for the two categories must be constant across all trials. The proportion associated with your outcome of interest is denoted as p. So, if you are looking at coin tosses, p might represent the proportion of times that you will turn up a head when flipping a coin. Or maybe you're interested in looking at the proportion of times that a student will guess the correct answer on a multiple choice test, strictly due to chance. The proportion of good guesses would be represented by p. As a result of the dichotomous outcomes being mutually exclusive and exhaustive, we can say that p plus q equals 1. Where p is the proportion associated with the outcome of interest, and q is the proportion associated with the other outcome. Because p plus q equals 1, we know that q equals 1 minus p. Most research questions that involve evaluating dichotomous variables fall into a special case of the binomial experiment called a Bernoulli trial. Binomial experiments, in general, require a set number of identical trials, represented as k trials. A Bernoulli trial, on the other hand, is a single trial, i.e. k equals 1, also with a dichotomous variable. So whereas a binomial experiment would be interested in whether or not a student guesses a particular number of questions correctly on a 10-item test, a Bernoulli trial would involve evaluating the proportion of times that a student guesses a particular question correctly. This is relevant when we start to think about the ways in which we will test a proportion. The center of a Bernoulli distribution is p, and the standard deviation is the square root of p times q. You'll recall that for interval and ratio variables, we denoted the center of the sample distribution with x bar. Sample statistics for proportions are denoted with a hat, so the center of the distribution of sample proportions is p hat, and the standard deviation of the distribution of sample proportions is the square root of p hat times q hat. This led us to the important realization that because of the way that the standard deviation of the sample distribution is calculated, variability will be maximized when p hat equals 0.5. Try a few numbers to see why this would be. If p hat were equal to 0.4, then q hat would be equal to 0.6, and the standard deviation would be equal to the square root of 0.24. If p hat were equal to 0.3, then q hat would be equal to 0.7, and the standard deviation would be equal to the square root of 0.21. The special properties of a Bernoulli trial allow us to use the z-test of proportions to evaluate whether or not a sample proportion is likely to have come from a population that is centered at a particular proportion. The z-test of proportions is constructed in pretty much the same way that the z-test of means is constructed. The z-test of means was constructed as the difference between a sample mean and a null hypothesis mean, divided by the standard error, where the standard error was defined as the population standard deviation divided by the square root of the sample size. The calculation of this inferential statistic allows us to draw conclusions about the probability of deriving a particular sample statistic in a population that is assumed to have a particular value, given a population standard deviation in a sample of a particular size. When we're making judgments about the likelihood of a proportion, we can use normal approximation, i.e. z-scores, to calculate the probability of drawing a sample with that proportion from within a population in which that event occurs at a rate that is defined by a particular proportion. As you can see from this formula, however, the standard deviation of the population is calculated using our knowledge of the distribution of Bernoulli trial proportions. But the z-test of proportions is still a sample statistic minus the assumed population value divided by the standard error, where the standard error is the population standard deviation, calculated as the square root of p null times q null, divided by the square root of the sample size. Although the z-test of proportions allows for a direct analysis of proportions in a way that can be presented in a conceptually intuitive way, we can also carry out these analyses using count data. Count data is often a better choice for the presentation of proportional data for two major reasons. First of all, it reminds the researcher to present the total n size. And this is very important because without the total n size, proportional data is entirely useless. You just know what the proportion is for a particular sample, but you don't know how many people were actually assessed. You really don't have a good idea as to how accurate that proportion can be considered to be. Secondly, using count data for the presentation of proportional data allows you to simultaneously compare more than two proportions. The z-test of proportions can only test a proportion against a hypothetical value. If you want to test more than two sample proportions, you're going to need to cast your data into a frequency count design. The statistic that we used for this analysis was the chi-square. For every cell within our matrix of count data, we need to compare the observed score, abbreviated here as O, with the expected value, which is abbreviated here as E, to see how different it is as a proportion of the expected value. Chi-square is the sum of all these cell comparisons. And with this introduction of the chi-square statistic, we realized that the chi-square is a test of model fit. It's quite a useful statistic, actually. You'll see it come up in all kinds of advanced analyses that require you to compare patterns of data across different samples, or when changing assumptions related to the relationship between variables within models that you use to explain your data. As we saw in weeks 4 and 5, the difference between two groups can be conceptualized as a correlation between a dichotomous grouping variable and an interval or ratio variable. And, as we learned in week 9, most analytic designs can be thought of as an independent variable predicting a dependent variable. Further, the analyses that we discussed in weeks 9 and 10 involved looking at the prediction of dependent variables using independent variables that are categorical in nature. But starting in week 8, we discussed methods for determining the association between two categorical variables. The first such association involved predicting change over time on a single categorical variable using a statistic called the McNemar test. Next, we expanded our lens on bivariate relationships to consider the association between any two categorical variables. All of these analyses are based on the same chi-square test that we just reviewed. Only the formatting of the data matrix has changed, bringing with it changes in critical values and the determination of expected values. If we're looking to calculate a difference between two time points on an interval or ratio variable, we can calculate a mean and a standard deviation, and our choice is clear, the dependent group's t-test. But what if your data is measured on a nominal or ordinal variable? As we've discussed, we are severely restricted in the mathematical operations that we can perform on nominal and ordinal data. We can't calculate a mean or a standard deviation. We can calculate a median, but only if the variable is ordinal. We can't even calculate a meaningful difference score. We need a new statistic, one that allows us to quantify change over time on nominal or ordinal variables. The McNemar test is best used in the assessment of change over two time points on a single dichotomous variable. It's probably obvious that this is a repeated measures analysis, given that it's intended to evaluate change over time, but nonetheless it's worth underscoring that this analysis requires that you survey the same group of individuals twice. To introduce the McNemar test, we looked at a simple example. You ask a group of undergraduate students whether or not they think that statistics are a useful component of the health studies curriculum. Specifically, they're asked, should statistics be required within the health studies curriculum, yes or no? You then ask the same group of students the same question after they've completed Health Sciences 3801. The instructor of the course is interested in determining whether or not exposure to statistical theory provides students with an appreciation for how useful the content can be. There are only two potential options within the question, yes and no, and there are only two time periods, before and after completing 3801. And we've satisfied the requirement that the data is arranged in a within-subjects design, i.e. we ask the question of the same students at time 1 and time 2. Thus, this is a 2x2 matrix of repeated measures data. We can use the McNemar test to assess the change from pre-test to post-test. The McNemar test is a test of change between our two time points, so let's think about the cells in our matrix within that context. Cells A and D represent individuals who didn't change their mind at all. Individuals within cell A disagreed with having statistics required within the health studies curriculum, and taking 3801 did not change their mind. Individuals within cell D believed that statistics was a solid requirement for the health studies curriculum even before taking 3801, and taking that course did not dissuade them from their belief. This leaves cells B and C as the cells that represent change. Individuals in cell C were of the mind that statistics was necessary for a degree in health studies, but after taking 3801, they changed their mind and decided that it should not be required. Before taking 3801, students in cell B were skeptical as to the value of statistics within their degree, but after taking the course, they were convinced of its value, ultimately coming to the realization that a day without statistics is like a day without sunshine. So, given that we're interested in change, we're really not all that interested in the individuals who are in the cells with no change in opinion. We're really only interested in the individuals who changed between time 1 and time 2. Now, consider that the McNemar test is, like all of the chi-square analyses that we've looked at so far, a test of model fit. We need to compare our observations to expectations. What would we expect our values in cells B and C to be under our null hypothesis? Well, if no one changes their mind in either direction, then the values of B and C will both be equal to 0. That's a pretty unrealistic expected value, though. At the very least, we would expect that there would be some random fluctuation in opinion. What we're really interested in is whether or not the probability of changing your mind from no to yes is equal to the probability of changing your mind from yes to no. If the probability of these two events is equal, then there's no effect of the independent variable. But how do we establish the expected value for these two cells? Well, consider what you would do if you knew that there were 30 students that changed their mind. We will consider the change from time 1 to time 2 to be random if the number of students changing their mind in each direction is equal. If there are 15 students who change their mind from yes to no, and 15 students who change their mind from no to yes. Because the total number of students who change their mind is equal to the sum of the cells B and C, and we're interested in testing to see if half of those students are in each of the cells B and C, we are setting the expected value of B and C to be equal to the average of the cells B and C. And from here on out, it's just a normal chi-square analysis, except Because we're only interested in the two cells that represent change on our dependent variable, we will only consider the difference between observation and expectation for cells B and C. The obtained chi-square for this analysis would be the squared difference between observation and expectation, divided by expectation for each of cells B and C. We would compare this to a chi-square critical with 1 degree of freedom. The McNemar test is very useful. It allows us to assess dichotomous outcomes in our most common clinical testing paradigm, the pre-test, post-test design. But it's a bit limited, isn't it? It's most appropriate for experimental designs that have only 2 time periods, and it only works for dichotomous variables. What if we want to test the association between 2 categorical variables that don't conform to the requirements of the McNemar test? For this type of analysis of bivariate count data, we need to apply a more general form of chi-square analysis, the chi-square test of independence. As we saw in week 6, we can test the correlation between 2 interval or ratio variables using Pearson's R. With ordinal data, we can evaluate the correlation between 2 variables using Spearman's rho. But what about nominal data? We hinted at this a bit when we introduced the concept of correlation, with something called a phi coefficient, but we didn't discuss methods for calculating this value. In week 8, we learned that the phi coefficient is closely related to the chi-square test of independence. Even this measure of association, however, is best applied to the assessment of 2 dichotomous variables. Thus, we'll need an additional statistic for some cases. With 2 nominal variables that may have any number of categories, we need to apply Cramer's V. In setting up for a chi-square test of independence, we need to arrange our data in a cross table. This is a matrix in which each of the cells represent the intersection between one level of each of your 2 variables. It's a table in which the levels of each variable are completely crossed, and this process is often called cross tabulation. As was the case with univariate analyses of count data, we're evaluating model fit. Our null hypothesis is that the variables are independent or uncorrelated. If variables are independent, then the assortment of individuals within the cells of the matrix should be random. Or rather, individuals should be arranged in such a way that the arrangement of individuals within the categories of variable A is not dependent upon variable B. In introducing cross-tabulation, we considered the association between 2 categorical variables, living arrangement and stage of Parkinson's disease, as measured on the Hone and Yahr staging scale. The rho marginal totals represent the number of individuals at each stage of disease. So rho 1 represents the number of individuals who are at stage 2 of the disease, rho 2 represents the number of individuals who are at stage 3 of the disease, and rho 3 represents the number of individuals who are at stage 4 of the disease. The column marginal totals represent the number of individuals